All right. Magnets. Is a piece of material that is able to attract certain metals. We have some elements that they just naturally have a property of being magnetic. Do y'all know any of them? Iron, nickel, cobalt. I heard somebody say cobalt. No, tin. Like there's metals that they are not a permanent magnet. And they could be like, some metals can be picked up, some cannot. The natural magnet is an iron ore called magnetite. That's how the magnet got its name. Okay, so look, I'm going to give y'all the chemical formula for that. Like I'm tying in our chemistry here. Y'all remember chemistry stuff? Magnetite is Fe3O4. Well, it'd be very important to know, yeah. Fe3O4 is magnetite. Magnets can be permanent or temporary. What does that mean? Huh? Not stick forever. Be magnetic. Yeah. Some things, okay, like a paper clip or a nail. I won't. Does that picking that up? What about this? No. But if I take the nail and like rub this magnet on it, I thought I had 3 paper clips, but see how the first time I picked it up the most though? Like, look, temporary. Okay, so look on page 722. they have what's called domains. All right? And if you look in the comb, what do you notice about the comb's domains? Yeah. And like they're all different ways. Look at the nail. They're a little bit lined up, yeah, but are the ends the same way as the S's? Look at the magnet. And they all the ends point the same way and all the S's point the same way. Okay? So in a magnetic material, the domains all align. What I did to that nail is on page 723. I messed with the atoms until I used the permanent magnet. The round one it's a strong magnet. It's a neodymium magnet or something. I don't even know how they say it, but this is a strong magnet. This magnet right here, it lined all of his domains up. Well, yeah, I mean, the more aligned I can get them, but it's not going to turn it into a permanent magnet. He's still only going to be temporary. Yeah. Wait, what? Y'all are going to actually do an experiment and figure out which materials are. Not today. Well, okay, I could have just let you do the experiment today, and then y'all would have been like, Miss Bro, I don't know what that word means. True, huh? Yeah. Well, if you didn't need me, I wouldn't have a job, but it seems like you kind of need me to tell it to you first, and then you can go do it, right? Yeah. What's up? Wait, what would? Yeah. Yeah, like, I mean, you start piling them up. Yeah, you're getting stronger. Yes, sir. The more magnets you have together, the stronger. Yes, that is true. Okay? A magnet has two poles. What are they called? A magnet is strongest at the poles. A North Pole never, ever, ever, never exists without a South Pole. That's a bar magnet. If he gets broken, What do I get? Break them in half. Huh? Never. It doesn't matter how small you try to break that magnet down to the tiniest little, it still has a north and a south. That is the major difference between magnet and electric. Look at 718. Hang on, let me get your question. Look at 718 and look at their picture. Their picture's way cooler than mine. See that? So, how is that different from electric? The electric charges. It's on the board. It's all around you, the answer. There's positive and negative. Say it loud. There could be a positive without a negative. That is the major difference between the two. Charges can be by themselves. Poles, never. Does not matter how small you go. You will have a north and a south. What was your question? Yep. If at the direct end of the south, right there, tiny, yep, north and the south. Because the whole thing is made of those domains. No, like, it doesn't matter where you are on the magnet, it's made of those domains. It went into little pieces, and then but they were still connected together. And that's weird, but that would make sense. That would prove that. That's now you just answered your own question. That's why I did that. Yeah, I've never actually broken it. Like, there's some pieces in there. I haven't had time though. But yeah, that would be cool. I'm going to probably try that now that you say that it did that. Does that make sense? But the reason why is because all those little norths and souths are still there. Any other question? Okay, last thing about this. Each piece we get is equally strong. Each piece is equally strong. Pretty cool? This is the globe. Okay. What are these two little sticky thingies? Poles. Okay. This is called geographic north.
Miss Brooks,
Yes, ma'am.
would you let Becca Lofton know that we have something for her in the office? To
Yes.
come by just at dinner class is fine.
Yes.
Thank you.
This bottom one down here is geographic south. Okay? Oh, why does it have to say geographic? Haven't you ever wondered why a compass, if you take a compass and the little needle points to the north, how does that actually work? Because I thought north and north repel. Okay, so you see those little dots that I just drew? Those are the magnetic poles. They're like off a little bit to the side of where the poles are. Okay? And the one at the top is called magnetic south. And the one at the bottom is called magnetic north. Because if the North Pole is really the north, the compass wouldn't go there. Wouldn't be attracted to it. Does that make sense? What you mean? What does that mean? I don't know. Does that only go for that place, or what do you mean?
No, you can use a compass anywhere in the world.
I'm so confused. Oh, it's okay. Don't try, because I'm like, what? Anybody else have a question? Okay. It's not you. I didn't understand what you were saying. Like, I don't get it. Because today they were telling me something about, well, then what's east and west? And I'm like, there's no east and west poles. Like, the earth is round, and they're like, I don't know. It's okay. My brain's just like, whew. Okay, we have magnetic fields just like we have electric fields. Yay! It's pretty much the same thing, okay? One difference though is like, I'm gonna have an experiment where y'all can actually do something to end up seeing the magnetic field, and there is nothing that I can do to make you see an electric field. Like, so, I don't want you to think that, like, you can't just look at this and say, oh yeah, I see the magnetic field, but it's there, okay? And we definitely can't see charges, but the charge is there and the field is there, okay? Yes?
You know this, where you stick your hand on the top of it and it looks like the lightning is attracted to your hand?
Yes. That is electric. Yes, we had a machine that kind of worked like that, the Van de Graaff machine, but we couldn't find a belt that would make it work for us to be able to use it in class. But yes, it's the same idea, because then your hair, yes. The region surrounding a magnet in which a magnetic field, force, a magnetic force can be detected. The force happens in the field. A moving charge produces a magnetic field. Fields create forces on moving electric charges. Objects do not have to touch to feel the force. This, a magnet, it has a magnet in it. These ends are the magnet, and you just hold it on the, it's like a magnetic wand thing. Y'all are going to get to use these and play with this. I just want to like barely move him. The pushing one, it'll never go to it, so that one. Yeah, I turned it over. Yeah. Bring it. I'll look at it. Yeah, I'm recording right now. Okay, so like this guy right here, I'm going to show you what it looks like. Yeah, you need this. This is a north. This is a south. How many? I think I did like this. My lines are all off today. Even this guy right here, like that, if we could look around him, he's going to have this, okay? This is his magnetic field. Weird, I know. You can also look on page 719 in the book, and it shows it to you at the top of the page, okay? This force goes north to south. 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 Bless you. If we had lines that were close together, what do y'all think that would mean? Just like the electric. The thing, I mean, like, even on the electric, it went positive to negative, right? And this goes north to south. Almost everything is the same, except for one thing. These go from him over here to south and through the magnet. Because remember how all those little domains were lined up in the same direction? And they all pointed towards the north? This is a closed loop, and the electric is not like that at all. Okay? So that is the main thing you got to know about this. Magnetic fields have no true end. Fields are closed loops that continue through the magnet. Does anybody have any question about this? And we're going to set up an experiment where y'all can actually see these. Okay? Okay, last thing we're talking about today, magnetic force. The attractive or repulsive force between two magnetized objects or on a charge moving in a magnetic field. Attractive or repulsive force between two magnetized objects, or it can be on a charge moving in a magnetic field. How do you get an attractive force? How do I get a repulsive force? Like or same. So that didn't change, did it? That's the same for magnets and electric. All right, the last thing we got to do is draw it. So what are these two going to do? What do I need to do for arrows? What'd you say? North to south. What are these two things going to do? Okay, but what does that mean? What kind of force is that? Oh, goodness, y'all. What's the definition of a force? What is this going to do? Push. So look, like, oops. They don't have to touch. Like, yeah, that was not good job. That's all uneven. That was a bad picture, sorry. Look at this one. This is better than mine. Make sense? Look at that one. See how it shows it through the magnet? Yes, ma'am. Yes, there's space because they don't want to touch. That is true.